Topic of this YouTube video is Chinese remainder theorem. This is very classical problem in number theory and useful to solve many numerical problems concerning residue system and divisibility of system and has several applications. So it is most important theorem in the number theory. So I selected this topic to make a video on this. So we require knowledge of divisibility here to understand this topic. So divisibility means we can say that we say uh, A divides B. A divides B. We write this A divides B reads A divides B. So and we write it mathematically. A divides B means there exists some integer C such that B equal AC. So we always consider both the number are positive. So C is also positive. So we say A divides B means that B is a multiple of A and C is a stage when it appears. So this concept of divisibility now further can be argued in terms of congruencies. Congruencies. In this we say A is congruent to two integers are there, A and B are two integers. So A is congruent to B modulo M. M is a fixed number greater than 1. If M divides A minus B, or you can say if M divides A minus B, then we say A is a congruent to B mod M. For example, we can say 12, and this fact is written as A is congruent to B mod M. We write this in this way. So we write like this. This is if M divides A minus B, then we write symbolically A is congruent to B modulo M. For example, here is example, if M is 12, M is 12. So we can take a number A, this is 17, and we can take a number B, which is minus 7. We can see that 17 is congruent to minus 7 mod 12. Okay, so because this is 24, if you take 12 divides 17 minus 7, and this is 17. Okay. So this is 24, this is 24, that is 12 is 17 minus 7. So we write this fact in this way. So we require, so this relation of congruence relation, this relation is in fact equivalence relation that can be verified easily on integers, set of integers. So this relation defines partition on the set of integers, but we are not going through this type of study about the partition. Now we deal with a problem that can be written like this. This is called linear congruency. So our interest is to solve this type of problems because such type of problems appears in many mathematical situation in research, and many competition problems also can be solved easily by knowledge of this problem. So this is a very old problem, linear congruence, this system of equation. So it is well known result and can be proved easily that if there are two positive integer, why we are taking two positive integer? So this is why we are taking two positive integers. So m is a fixed integer here. So m is a fixed integer. So you can see that this is m. Okay, this is GCD of em. This is correction in this. D is GCD of am. D is the GCD of am. So this is a statement. This problem has a solution if and only if D divides B. And in such a situation, if D is 1, then it always divides. So if B divides, I think this is okay. So so you can see here, if D is 1, then it divides B always. So in that case, it has a D incongruent solution. So our problem is to solve this equation. Solve this equation. This is okay. This can be corrected like this can be corrected. This is M. Okay. This is M here. So we want to solve this problem. So I think this will be very easy. So we come to prove. So first we consider the situation when we are taking that this is this congruence. Write the congruence. So you can see that A is congruent to B mod M. Then it can be written as M divides ax minus b, and hence we can write ax minus b equal my for some integer m. So we can write this congruence like this. This is a well-known Diophantine equation. So let this Diophantine equation as a solution. So we want to show that if this Diophantine equation solution, then x naught will be the solution of this problem. So this Diophantine equation has a solution. It means that there exists integer x naught and y naught satisfying this condition. Since now we know that D is the GCD of AM. D is the GCD of AM. So D can D divides A and D divide M. So we by the definition of divisibility, A can be written as a DA1 and M can be written as a DM1 for some integer positive integer A1 M1. Then you can see that D divides A and D divide M, or certainly D divides this right hand side because it is dividing left hand side. So we have proved that if this type of equation, this type of system has a solution, then D must divide the greatest common divisor of E and M must divide B. Conversely, we can think about D divides B, then we will show that this system as a solution. So most important part of this theorem is that whether the system of equation this has a solution. So first we should verify this. Like if you take 3 3 x is congruent to 1 1 mod 55. So if you have to check this, so we can solve this system because you can see that uh, this is the system. So So whether we can check this system as a solution or not. Like other simple situation is this 3 mod 5. So we can see that 7 and 5 GCD is 1, or if you take here 10, then you say GCD is 2. Okay, GCD is 2 and 2 is not dividing 3. So this type of system has no solution. So this linear congruence has no solution. So whether the linear congruence has solution or not, it must be verified this thing. So D divides B. So we have assumed that D divides B. So B can be written as DBM by the divisibility. Now D is a GCD of AM, and therefore we can write D in linear combination of A and M for some integer R and S. Now if we multiply this B1, then we will get B here. Left side becomes B, and right side is A B1R plus M B1S. So you can make it here. This is this can be taken as x naught, this taken as x naught, and this taken as a y naught. So you can see that B can be written as ax naught plus my naught, and therefore we can write this ax naught minus b is a multiple of m. Therefore m divides ax naught minus b, and hence we have this situation. It means that ax naught uh, x naught is a solution of such congruence in case when d divides b. Next part is how many distinct solution, incongruent solution. Distinct means incongruent solution, because this system has infinite many solutions like this. If x naught and y naught we find x naught y naught is one of the solution, then such if we consider x like this, then that must be a solution. So for every integer t there will be a solution. So we are interested in incongruent solution. So incongruent solution can be found in such a way. Consider two solution x1 and x2 of this. We consider two value of x. So there will be, because x naught is fixed, m and d are fixed, so there will be a t1 and t2 corresponding two values of x. So x1 can be written as this. If we consider these two are m, congruent modulo m, then we will see that this can be written as md by d. This can be, so md will divide both of side. So we will find t1 t2 is also congruent to modulo d. Means that if we are considering x1 is congruent to x2 mod m, then we must have t1 congruent to t2 mod d. So if these two number are congruent, then t1 t2 will be congruent modulo d. It means that there will be d distinct congruence classes, and therefore there will be d distinct congruent congruent solutions. So thus there is d distinct solution, and conversely. So now we come to our problem, Chinese remainder theorem. This is a system of equation. It is given that x is a number that we have to determine that leaves remainder even when divided by m1, a2 by m2, and ak by mk. And these all m1, m2, mk are relatively prime. Uh, so we can consider a number m that is a product of this. So this system of equations individually can be solved. So now we are interested to find a unique x that satisfying all the congruences modulo m. We have to find a unique x. Actually we need to find, we need to find a an x, okay, an x satisfying all the congruent. Okay, satisfying all the congruences. So you can see here next slide, we are giving this an example here. So we can say, if we consider a problem like this, so we are interested in finding the solution of this problem, where we have to find a number x that leaves remainder 1 when divided by 3, x when leaves remainder 2 when divided by 4, and divided by 5 3. So we a1 a2 a3 are as follows: m1 m2 m3. So now the proof of Chinese remainder theorem will follow in the same way as we are solving this problem. So first of all, we consider m. M is a product of m1, m2, m3. This is 60. Capital M1 is 60 divided by m1 means 20. 60 divided by m2 means 15, and 60 divided by m3 we will divide it by 5, 12. So we have these number. Now according to these number, now we know that mi is co-prime with mi, because we are obtaining this is 20 when divided by m1. So it means that m1 and 20 are relatively prime. So it means that mi and mi relatively prime. So our previous theorem that we have proved, this system mix congruent to 1 mod mi has a solution. So this system has a solution in that case. So we created a system, well-known system, that has a solution. So how we created? Because we know we have already done ax is congruent to b mod m has a solution if and only if GCD of A and M, GCD of A and M. Now we have, this is now M1 and this is small m1, and we know that GCD of this both are 1. So 1, so obviously we can take here 1, then this system has a solution. So this system has a solution. This system has a solution, so we can write name of solution is xi. So xi, so we have three solution: x1, x2, and x3. m1 x1 is congruent to 1 mod m1, and we have 3 x1 x2 x3. So now we can make a linear combination like this. a1 is given, m1 is given because small m1 is given, and x1 we have determined by solving this equation. And if we taking this all in account, so we will they see that this is satisfying this equation. If we divide this expression by 3, so you will see that m3 is a multiple of 3, so it is 0. m3 is a multiple of 3, so it is 0. m2 is also multiple of 3, so this is it, 0. And m1 x1 is 1. m1 x1 is 1, so this becomes e1 mod 60, or you can say 3. So this satisfying this condition. So after substituting these value, you have to fix x1. Actually you have to first find x1 x2 xn, and you can substitute these value. There may be several solution, then it is up to your choice what solution you require. So this system has a solution. So in the same way, in this proof I just changed 3 by key, and in same way we can find a linear combination that meet the requirement. So I think this proof is quite easy, and this is a very useful theorem, and in many mathematical situations, like and everywhere, like when we are studying pure mathematics, linear algebra, group theory, and many other situations where modular system uh, is present, this theorem is important. So I think this is good idea to solve some more problem, including this also. So you need to find the solution. There may be infinite, there may be finite many solution, but there sometimes our requirement. So because of such x is not unique, such x is not unique, but The least value of such is unique. So we sometimes we interested in the least value. Okay, so this the proof is very easy. In fact, we have a problem. X is congruent to a1 mod m1, x is congruent to a2 mod m2, x is congruent to ak mod mk. So we created first of all mi. Mi is m upon mi, m upon mi. And after getting this is a very straightforward. This these two numbers are relatively prime, and these two numbers are relatively prime. So by this congruent, this problem has a unique solution. This problem has a unique solution. This problem has a unique solution. You can write this solution is x1 xi. So collect all xi's, collect all xi's, ai's and mi's, capital mi's are already there, already given. So make a number by using the combination of this, and that number will be your solution of Chinese remainder theorem. Okay, thank you.